Welcome to solverfy.
So, in part A, we can directly apply the conservation of energy where Kf is the final kinetic energy and Uf is the final potential energy, which should be equal to K initial or initial kinetic energy plus initial potential energy. Now we can see that when the bag is totally inflated, then there's no final kinetic energy. So we can safely ignore this part. Similarly, the initial potential energy will be zero when the bag starts to inflate. All we have is the kinetic energy because the bag is starting to inflate at that time. So this kinetic energy will be half of mv naught squared, where v naught is the speed of the driver, and for the potential energy, it's uf is when um, uh, yeah, uf is when the bag is totally compressed. So or yeah, so when the bag gets maximum compression, we say uf is equal to half of k x max squared, where x is the maximum compression and k is the spring constant. So let me make this k a small k so that we don't get confused with the kinetic energy part. So using these two relations, we can set them equal to each other. So half of mv naught squared should be equal to half of k x max squared, and from there, if we get rid of half, we see k is equal to mv naught squared by x max squared. Now in part B, we need to find out the maximum force. So for maximum force, we can use k times x max, where again k is the force constant. So since we have already figured out this relation of k, so we can substitute um, k by f over x max. So if we set k equal to f over x max and put that in this equation, so here we'll just write f max over x max and solve for it. We see that f is mv naught squared by f max. In part C, we'll just be using the numbers for v, m, and x max, and we see that the maximum force will be 1.25 times 10 to the 5 newtons. And to get the force constant, we can use this equation right here. So k will be the maximum force divided by the maximum distance that's traveled by the airbag, so which is 4.2 times 10 to the 5 Newton per meter. And also, if we want to calculate the velocity, we'll see that we can use this equation right here, where we'll just solve for velocity in terms of the other parameters. And we see that we have f max times x max by m, because again, that equation has been changed to this equation, where if we write that in terms of v naught, we'll see that v naught should be equal to square root of f max times x max divided by m. So what we did here is we multiplied x max on both sides and then divided m on both sides as well, and then we took a square root because there's a square sign over here. So that's what gave us this expression, and if we put the numbers again, we see that it's 24 meter per second, which is 54 miles per hour. And in part E, if like we want to design a safer airbag for higher speed collisions, we need longer distance X max, because we see that if we increase X max, then F max will be increased. So that will create a safer design. And also, what things we can alter is we can extend the gas, brake, and clutch so that we have a further distance between the steering and us. And also we can decrease the stiffness of K of the airbag, because if we decrease the stiffness, then um, this will reduce the maximum force, so that will be safer for us. And if we make stiffer airbag, that will increase the force constant, and also that will increase the F max, which will be less safe for us. Thank you.